Okay, so the last thing that we're going to do for logarithms and exponentials is applications. Now, the two major things that we're going to need are, the first is converting between index and logarithmic form. So for example, 2 to the power of 3 is equal to 8 is equivalent to log base 2 of 8, which is equal to 3. And we'll need the change of base. So for example, log of base a of x is the same as log of a different base b of x over log of that different base b again of a. And remember, back when we did this, we were particularly looking at logarithms of base 10 because that's what our calculator can do. So because it's applications, we're going to jump straight into an application. And here is our application. So the population of a country is tripling every 45 years and was 150,000 at the last census. So explain why the population P after another year is just can't seem to scroll this one down. That's all right. Okay, so explain why the population P after another n years is P is equal to 150,000 times 3 to the n to the 45. Well, the reason it's that is because the reason it's this is because there are n over 45 segments between, or I should say each 45 years. Okay, so the reason why we use the n to the 45 is because there's 45 segments, okay? So think of it like, if we were to work out, well, when does it first triple? So 3 to the power of 1s, it's 45 over 45 after 45 years, okay? So there are n over 45 segments between each 45 year gap, I guess you could say. Part B, find the population nearest 100,000 after 90 years and 100 years. Okay, so that's part B. Now we're going to use this equation up the top, which is P is equal to 150,000. So P is equal to 150,000 times 3 to the power of n on 45. Okay, and the reason why we're using this is because, it's the formula they give us, and we need to find the population. So what we're going to do is we're going to substitute our values into this equation. So for first one, it is 90 years. So we're going to go P is equal to 150,000 times 3 to the 90 over 45. So it's so in this case, it should, triple twice. So it's 150,000 times 3 to the power of 90 on 45, or just the power of 2. Okay, and the population is going to be 1.35 million. So it's 135,000,000. Okay, so it's 1,350,000. And we need to do it to the nearest 100,000. So the population is equal to 140,000 to the nearest 100,000. Okay. Part 2 is 100 years, so 10 more years. So P is equal to 150,000 times 3 to the 100 over 45. So population, put it into our calculator, because I already have this one here ready to go. Put it in, and this one's a little bit more, well, not as nice, but it's 1.72 million, 1,723,299.3, blah, 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 whatever. But to the nearest 100,000, it's going to be 170,000. Now, obviously, in real life, that's not going to be an exact number. Like, these aren't going to be exactly, it's not going to exactly triple after that amount of years, but hey, it gives us a good idea. Now, by substituting into the equation, find the nearest year when the population will be 48 million and 60 million. Okay, so that's weird. Doesn't want to write that. Okay, So again, we're going to use this population function times 3 to the n on 45. But this time we want to find what n is equal to, okay? So we want to find the number of years. So our first number is when p is equal to 48 million. So we get 48 million is equal to 150,000 times 3 to the n on 45, okay? So we're going to start off by dividing both sides by 150,000 to get the 3 to the n on 45 by itself. So it's going to be 48 million, over 150,000, and that's equal to, why have I put the times there? That's weird. That's equal to 3 to the n on 45. Now, remembering from the other days, if I want to get the n, the 45, on its own, what I'm going to do is I'm going to take the log 3 of both sides. I'm going to take log 3 of 48 million. So remember, 48 million over 150,000 is just a number, and that's equal to log 3 of 3 to the n over 45, okay? Oh, not quite like that. The n over 45, like that. Okay, now that we've got a power of a power, what we're going to do is take that power to the outside. 1, 2, 3, 1, 2, 3 over 150,000, and that's going to be equal to, so the log 3 and the 3 cancel out, and it's going to leave us with n on 45. Now to get the n by itself, we're going to multiply it by 45. So 45 times log 3 over the 48 million over 150,000. Now remembering again that log 3 of the number in there is just a number. So we're going to use this change of base, which is log, and we're going to use base 10 because that's what we want. So remembering that what we've got as our value for x here is just this whole number here, okay? It's that whole number. And our base is our 3. So when we rewrite this to put in our calculator, we're going to do 45 times, okay? Now we're going to do a change of base. So it's going to be log 10 of 48 million over 150,000, because remembering that's just a number, over log 10 of 3. Okay, so that's our change of base, so we can put it in our calculator. So that is going to give us n is equal to, so 45 times, and I'm going to go fraction log of 48, 123, 123, over 150, 123, close off the bracket, and we're going to put it over log, remembering that the calculator does it in base 10 for us, and we're going to get 236.27 years. And to the nearest year, that means that we're going to have 236 years, which is quite a lot of years. But if you're thinking of a town that starts off at 150,000 people, it's going to take a very long time before it gets to a really big sort of city like that. So that's a huge city. Okay, so continuing on with part C, 2. So we're going to do it for 60 million now. So it's going to be basically the exact same method. Okay, so so let's write down the formula again, which is P is equal to 150,000 times 3 to the n on 45. So the population in this case is, we want it to get to, this one is 60 million. So therefore, 60 million is equal to 150,000 times 3 to the n over 45. Divide both sides by 150,000, so we're going to get 60 million over 150,000 is equal to 3 to the n on 45. Now again, we want to get that n45 by itself, so if I take a log 3 of both sides, it's going to push that n45 down in front. So take log 3 of both sides, remembering that 60 million over 150,000 is just a number. Okay, we could simplify it, but I'm not going to bother. I'm going to leave it in its whole form, and that's going to be equal to log 3 of 3 to the n on 45. Now remember, when we have a power rule, So remembering that rule is actually just log whatever of x to the p is just equal to p lots of log 3 to the x. So remember, it's that rule that we're using to do this thing. So on the left, we've got log 3 is equal to 60 million over 150,000 is equal to log, the logs are going to cancel out, sorry. Logs are going to cancel out. I'm going to be left with n over 45, okay? So multiplying both sides by 45, we're going to get n is equal to 45 times log 3 of 60 million over 150,000. Okay, and now we're going to do that change of base again so we can put it into our calculator. So it's 45 times log 3. Sorry, not log 3. In this case, it's going to be log... Actually, we'll write it as the fraction. So it's going to be log 10 of 60 million over 150,000 over log 10 of 3. So n is equal to, and so I can go back up to this one because everything has already been pretty much put in there for me, except for the 45 needs to change to 60. And this one here is 245.41. So n is equal to 245 to the nearest. Yeah. Now, it doesn't seem like that much more than the other one. So the other one was 236, and this one's, gone from 48 million to 60 million in, less than 10 years. But that kind of makes sense. Think, like, this thing is exponentially growing, okay? Once 45 years has gone up, it's gone from 150,000 to triple that, which is 450,000. But then from the 450,000 in the next 45 years, it's actually going to triple from there. So from 450,000, it will triple in the next 45 years, and it's going to give us the population, which we worked up in part B, which was 14 million. So, like, it's jumping up, it's exponentially grows, and that's how exponentials work. So with that being said, that's all of the stuff that we need to do for this one. Okay, so it's all basically, this whole exercise is basically just about applying these different types of exponentials and logarithms and getting answers that we want. So with that being said, that's going to conclude this video, and that concludes this topic. So our next topic that we're going to do is going to be the calculus, the beginning of calculus, where we look at differentiation.